And welcome to our presentation this afternoon on risk and uncertainty. Certainly a very timely article. Our speaker today is Dr. Peter Dekker. Peter studied marine geology at the Free University in Amsterdam. His professional career started with Shell International in the UK, working on both the North Sea and the West of Shetland Exploration. Then he moved to the Middle East, Oman, where he gained experience as a production geoscientist. Then in 2001, Peter joined Preussag as Chief Geologist. Then he went to Gaz de France, where he was the Global Exploration Manager in Paris. Subsequently moved to South Africa, where he has worked for Sasol and is currently Chief Geophysicist at PetroSA. And during his career, Peter has been involved with reserve and resource estimation for various companies. He is currently also the chairperson of the SAMOG Code Committee and an observer on the IMVAL Committee. And as such, Peter is well poised to talk to us about risk and uncertainty and its application within the hydrocarbon exploration and production industry. Peter, thank you very much.
Thank you very much, Tanya. Thank you, everybody, for coming online. This is a short presentation, which is kind of a spin-off of a presentation I heard last week, where people were talking about uncertainty and confidence levels. And there is in the various industries a big different view on what is uncertainty and what is confidence level and what is risk. And I thought it might be kind of nice to talk to the GSSA about risk and uncertainty and confidence levels within the oil and gas industry. There are quite a lot of mining people, member of the GSSA. And I think that we as two different industries can learn a lot from each other. So I hope also somewhere in the future to learn more about risk and uncertainty in the mining sector. But this time I will show you guys a little bit how it works from the oil and gas side. So to start there, let me see if it works. I try to go with next slide. Maybe this works. Yeah. We as geoscientists in these industries and also the engineers in industries, we've never had formal training in effective estimating. Yeah, we've had very good formal training in mathematics, in physical science, computer science, geological principles, and engineering, all the things. But who of us has really learned how to make estimates and how to really assess from how much is really there? And that all comes from experience working in the industry, working with the data. But at a certain moment, we will see that we all diverted in different directions. And there's not really a system what we are all following. I was lucky enough early in my career to follow a course where we were trained in it. And some of these slides I'm going to show you today are based on that course. And at the end, I will show you also the book of that course, which is quite useful to read through. But before we go there, I think it's a nice experience for all of us to have a little bit of an experience in an exercise from what I mean. And as I said, we first start with risk, and then we come to uncertainty. Now, the risk is, of course, the probability that something happens or doesn't happen. So I'm going to show you some slides, a slide now, and the slide might contain some soldiers of the Terracotta Army in China, or it might contain something else. So I would all of you now to try to think for yourself, what is the probability that the next slide is going to be the Terracotta Army in China? Just think for it for a moment. Is it 50-50? Is it 70-25? So 70% chance that I would show the slide or not. Now I'm going to show you the slide, and it is not the Terracotta Army, it is the Chinese wall. So that is the risk. You know, there was a risk that I would show something else than the Terracotta Army. I was after the Terracotta Army, but I didn't show you that slide, I showed you the wall. So anybody of you said that I would show the Terracotta Army missed it. It was an either or. So that is the risk I talk about. Now I'm going to talk about uncertainty. So my next slide is really going to be the Terracotta Army. And my question to you guys will be from how many soldiers do you see in the next slide? I'm only going to show you the slide for 10 seconds. So in 10 seconds, you have to make an estimation of how many soldiers you will see there. And this is already where we come to our uncertainty, because you cannot be certain because you won't be able to count the amount of soldiers in 10 seconds. So are we ready? I'm going to show you the slide now. Okay, now I say thinking time. So you had 10 seconds the time to check the amount of soldiers, and probably you counted 20 or so, you saw the area and you multiply it with the rest around there. But I'm sure of you that all of you have got a different number. Yeah, nobody, maybe 2 or 3 people might have a similar number, but nobody will have the same number as the real number. The real number is 202 soldiers in that picture. So now you can make an assessment for yourself how far you were away from the 202 soldiers. So what are the lessons we learned here? Yeah, there was a risk of no soldiers, and that risk occurred in the first slide. Yeah, so we didn't find any oil. We thought we were going to find oil, the soldiers, we didn't find the oil. We found nothing. In the second slide, we did find the oil, but now we had to estimate how much oil there was. And we had to make an estimate of it. We will never know exactly how much oil there is, but we can make an estimation. And that estimation you give a real value in with a certain level of confidence, which I will discuss later in the presentation. Yeah. What we also learn from here is the less you know about the subject, the wider your range of possible outcomes should be. So if I ask you how many soldiers there are, should you give one number, or should you say, I think there were between 150 and 250 soldiers? If I had a very short time to guess, I might say between 100 and 300. If I had longer time to estimate, yeah, I say I had not 10 seconds, but I had 30 seconds, I might say between 180 and 220. So depending on how much time you have, about how much you know about the subject, you can give a wider range. Yeah. So what is risk? A few definitions. In 1921, Frank Knight said, risk is the randomness of a knowable property. It's a simple choice. It's either there or it's not there. So it's an on-off switch. You either find oil or you don't find oil. And you give a probability to that. And we'll come back to probabilities later. So the risk is yes or no, on or off. It's there, it's not there. Uncertainty is the randomness where we cannot know the properties. It's a complex choice. Variety of outcomes is infinite. You give a range of possible outcomes. Yeah, it's a whole range of it. So we will go more in detail in uncertainty later, but first let's go to, let's first come here. So in essence, what we say, for example, if there's a 60% chance to find oil, you can see there's a 40% risk that we will not find oil. On the left side of this graph, you see the 40% risk there. And there's a 60% risk to find some oil, but you cannot say how much. So the 60% is to find 0.1 barrel or more. And keep that in mind, the or more thing. It's not 60% to find 100 million or 200 million. No, it's 60% to find more than 1 million barrels of oil. Yeah, so that is your probability of success. And your uncertainty is then how much you want to find. Now we're going to come, here risk and uncertainty analysis does not find hydrocarbons for you. It helps you in doing your economics and doing your risk assessment, whether you should drill a prospect or not, whether it is risk balanced and whether the chances that you're successful will pay for the times that you will not be successful. To find hydrocarbons, you still need detailed analysis, good geological insight, imagination, and of course, in the end, you have to drill. Without drilling, you will never find oil or gas. So what is risk? Risk analysis is the assessment of confidence in the geological factors required for successful exploration for oil and gas. To be successful, you need a source to generate oil and gas. You need a trap and a seal pair. You need reservoir, and you need migration, and the timing of migration has to be right to trap it in the oil and seal. Each of these elements have got a risk factor that they are there or they're not there. And for example, these risk factors are not, you multiply with them. So if I say there's a 50% chance that I've got a source rock, I've got a 50% chance there's a trap and seal, I've got a 15% chance there's reservoir, I've got a 50% chance there's migration and timing is right, then the total chance of finding oil is 50 times 50 times 50 times 50. That's only 6%. So then my probability of success is only 6% to find oil or gas. Because all of them have to work, and that's why it's multiplicable. Now, risk management is, of course, to identify the main risk and find mitigation plans, how I can reduce the main risk. So, for example, if my trap and seal is 50%, and it was based only on 2D seismic, I might want to shoot a 3D seismic survey. And on a 3D seismic survey, I get a much better definition of my trap and my seal, and my risk might reduce from 50%, of my probability of success might reduce from 50% to 90%. So I've got a 90% probability of success. And that, of course, will increase my total probability of success. Yeah, but there will always be inherent risk in anything we do until the moment you drill it and the drill bit comes there. But even then, sometimes people have got different interpretation of what was found. Now, the probability of success I've just showed you is pure technical success. So it is the geological success, the success of development. Can we develop it? Can we build the structures and all the things? In addition, there's of course also commercial success, economic, political, commercial, all the other success factors which count. And in the end, for projects, both of them have to work, of course. Let's now go to uncertainty and estimation. Yeah? In oil and gas, we quite often speak about the expected ultimate recoverable. I think that's the same like in mining. When you start mining, you only recover a little bit because your mine is not completely developed yet. But of course, in the end, when you do projects, you want to know what is the final I can get out of it before I close the mine. And that's what we call the expected ultimate recoverable resources. Yeah, it's a subjective estimate, but that's why we are paid the money. Because of our expertise, we are expected to give right estimates for that. And that's where estimation comes in. Yeah? The EOR is not only fixed by geology and laws of physics, but is also increased and decreases by the knowledge growing of us. You learn more about geology, technology changes, you get much more technological tools to get more out of the underground, like fracking we spoke about. And of course, the economic changes. Yeah? In economic changes we could see today where the Western Texas intermediate oil went to negative even. People had to pay money to get rid of their oil. So then nothing will be economic. And then of course your ultimate recoverable will be zero. You don't want to produce anymore. Yeah. Expected ultimate recoverable resources are often wrong because we don't realize or imagine the significant heterogeneity of the reservoirs and the other uncertainties all around it. But we still have to give it because we want to do our economics, we want to do our project planning, and we need to know, do we want to drill this prospect or not? And we ask geoscientists to estimate the expected ultimate recoverable with hardly any data. Yeah, we all know, also in mining, there's hardly any data. And to understand what I mean with this, I'm going to do another exercise with you. I'm going to show you 3 slides. The last slide is a photograph of an area. And the other 2 slides are coming from that photograph. The first slide is only 10 pixels made from the photograph in the end. And these 10 pixels can be seen as 10 wells drilled. Also like in mining, you drill 10 wells, you don't know where the minerals are. But we are still asked to make an estimate from what is where in the underground. And then we make models. So the second slide is going to be a model made based on the 10 pixels. And I'm going to ask you all to answer some questions there. So let's go to the first slide now. So this is the first slide. You can see 10 pixels here. In the top, you see 1 pixel, which is a light colored cloud. You see another pixel, also a light colored cloud. Then you see a pixel, which is a piece of a rock. You've got a dark colored cloud. You've got another rock, which is dark. You've got a light rock. You've got some grass. You've got some massive grass. You've got some dark grass, and you've got a house. Now, this is all very nice, but now my question is going to be, based on this, how many houses do you think there will be here in this picture? So I'm going to leave you for about 10-20 seconds to make your estimate. Based on these 10 pixels, how many houses do you think there will be around? So in that, we would normally try to make a geological model, a static model, and in oil and gas, from static models, we go to dynamic models to see how things flow. And this is the model we made. So by having these pixels, we extrapolated, interpolated, and went all around. And now you can see that there are 57 pixels with houses. And of course, not every pixel is a house, because the one pixel was part of a house. And now we as geologists are asked from, okay, how many houses are represented by these 57 pixels in this model? Yeah.
Okay.
Sorry? Okay. Yeah, do you want to give one number? Do you want to give a range of number of houses? That's the whole question. Now for yourself, you can make up your mind, but let's go to the last slide. And the last slide is the real picture. So this is the picture from where we got all the pixels. And you see, some of the trees were missing. There were in total 6 houses around. Yeah. And did we really have this picture in mind when we had made our model? I'm not so sure we had it. But of course, the important thing is that we were asked to give an estimate of the amount of houses. And that's what we asked from our geologists to do. Philip, have you got a question for us?
Okay.
Okay. So now in making these estimates, there are 2 ways of doing it. There is a deterministic way and there's a stochastic way. Now in deterministic ways, you really give one number per well drilled. So you say how much oil or gas will you discover per well. And you can either overestimate or underestimate, or very rarely will you be exactly on the level of the wells.
Okay.
Philip, can you mute yourself? Yeah, thank you. And so you will never really get the real answer because it's such a big range that it can be, but you will be either further overestimated than other ones or closer to it. But of course, it's much better if you can give a range within you think the actual number will be. And to come to these ranges, we do stochastic estimation. And stochastic estimation, for that we need some input parameters. And we come to statistics and we come to distributions. I see a question. I will come to the questions later, maybe, Tanja? Okay, that was there. No problems. So let me go back one slide. Okay, so in oil and gas, if we want to calculate the volumes in play, of the volumes produced, we need to know the area, we need to know the thickness, we need to know the net to gross, the porosity, the saturation, expansion factors, recovery efficiencies. There's a lot of elements. And all these elements are multiplied with each other to come to a number for your volumes. Now in that, we're going to just show you a little example how we do it. I'm going to use 4 dices, and we're going to throw 4 dices. If we throw the 4 dices, we multiply each of the dice. So the lowest number is of course 1, because if all 4 dices throw 1, 1 times 1 times 1 times 1 is 1. Yeah, the highest number you can throw is 1296. That's if all dices are 6. And if you now look on the graph, and you go completely to the right-hand side of the graph, you see there's only one little tick at 1. That is if all dices throw 6. There will be one little tick completely on the left at number 1, and that is the 1. And then, of course, if you throw 1, 5, and for the rest 6s, you come somewhere to 1060, I think, and that is here. So these are 4 cases, and here you will have 4 cases as well. But in general, you get a graph which looks something like this with all possible outcomes. And this graph tends towards a log normal graph. And the log normal graph is a natural graph which comes from multiplication of distributions. If you got distributions, you multiply them, they always tend to go to log normal graphs. And these are types of graphs we are very much used to in the oil and gas we use for our estimations. To make it a little bit simple and in a different type of presentation, we're going to go to 2 dices. We're going to throw 2 dices. And of course, with 2 dices, you only got 36 outcomes. And I've plotted these 36 outcomes here in another display. It is a graph called the probit scale. It's logarithmic horizontal. And on the vertical, it's a double logarithmic around the P50 in the middle. The P50 is the 50% chance of occurring. And then the P99 is the 99% chance, and the P1 is the 1% chance. On the left scale, you will see at the bottom it starts with P1, going up to P99. And on the right-hand side, you'll see at the bottom it starts with P99, going up to P1. This very much depends on what type of company you are. I'm used to work in a company which we call a greater than company. That means we use the right-hand scale where the bottom is P99. So in essence, what it says is you've got a 99% chance, so a 100% chance to find a value bigger than 0. And that's clear. In essence, here you see you've got a 2% chance, of a 2.6% chance to find a value bigger than 1. And that's clear because you throw 2 times 1, that's 1. To find a value bigger than 1, you've got a 2.6% chance to find it, because that is, of course, 97, not 2%, sorry, a 97% chance to find bigger than 1. That is 35 over 36. So all of these are bigger than 1. So you've got a 97% chance, you can see that on the right-hand scale here, to find a value bigger than 1. And that's how we use these scales. And I will come back to this scale later. So in essence, what you can also say, you've got a 50% chance to find a value bigger than 10. You see, at the P50, you go to where you see the graph and you go down. So you've got a 50% chance to throw a value bigger than 10. That's how we use these graphs. Now, the nice thing of log normal curves is that they've got a few things you can always read from them. So in essence, one of the things is the mean is always bigger than the median. And I will show you later what the mean and the median is. They've always got a skewed tail. So they've got a big high side in the beginning and a very long skewed tail. Very small chance for high outcomes, but they can happen. The uncertainty is the P10 over the P90. That's always how we express uncertainties. And very nice thing is that the P10 over P50 is the same as the P50 over P90. That's how you can always identify log normal curves. Now let's go to the mode, the median and the mean, because we always give more numbers, but if you are asked to say which number to use, the mode, if I go back up here, the mode is this highest point, that's the most occurring point. The median is the P50, that's this point, and the mean is somewhere out here, is that point. So the mode, this event or interval with the highest probability of occurrence, it is the highest chance that it will occur. The median is really where you've got the same amount that it will be higher, the same chance it will be higher as the chance that it will be lower. So the mode you use if you only deal with one single event. The median you consider when you two events are equal. And the mean is really when you do portfolio management, where you look at averages and sums and all the things. So we have to keep it in mind with log normals that there's a difference between mode, median and mean. So what's now the confidence level? Let's go back to this graph. If I say I want to give a confidence level of 80%, you saw the graph already, we saw earlier, we had one point down here and went up all the way. So if I give you two numbers, I give you this number and I give you that number, I'm for 80% confident that the real value will lie within these two numbers. There's a 10% chance it will be bigger than this number, and there's a 10% chance it will be smaller than this number. So I've got 80% confident that the real number will lie between these two numbers. If I now go to our dices again, our two dices, yeah, I'm 80% confident that my real number I will throw will lie between 3 and 25. There's a 10% chance that the number will be smaller than 3, 1, 2, 3. There's a 10% chance it's smaller. There's a 10% chance it will be bigger than 25. So when I'm now asked to give an 80% confidence level, I say if I throw two dices, for 80% of the times, the multiplication of both dices will lie between 3 and 25. So if I say throwing the dices is the amount of oil I will find, and I tell my executives that I'm for 80% confident that the lowest amount of oil I will find is 3 million barrels, and the highest amount of oil I will find is 25 million barrels. There is still a 10% chance I will find less than 3 million, but that's what we take as granted. And there's still a 10% chance it's bigger than 25, but that's what we take as granted. So my low is 3, my high is 25. Yeah, so now I've got a question for you to test this. Yeah, how long is the River Nile? You don't know about the Nile so much, so give me your 80% confidence level about the length of the River Nile. So in essence, if you all would give me a number, I expect, not a number, a range of numbers, I expect that some of you will be below the real thing, some of you will be above it. So if I ask you your 80% confidence level, I don't want one number, I want your P90 length of the Nile and your P10. And the more certain you are, the narrower your range can be. The less certain you are, the more uncertain you are, the wider the range should be. Now for you, the Nile is 6,650 kilometers long. So if you had an idea, you can see whether you were falling within, whether your range was covering the real length of the Nile. So if your P90 was lower than this and your P10 was higher than this, you were right in your 80% confidence. If you were not right, then you were some of the 10% guys. And I think that was, in essence, all I wanted to say. These are the two books, Risk and Analysis and Management of Petroleum Exploration from Pete Rose. That is a course he gives, a very, very good course to follow. Or Against All Odds. These are two very good books to read if you want to learn more about it. And I think that was my presentation, just within half an hour, but I'm open for questions.
Thanks very much, Peter. Any questions or comments? You can raise your hand and unmute your mic. I don't see any questions or answers.
Craig?
Yeah, Andy.
Yeah, Peter, very interesting. But when we calculate volumes, we generally calculate a volume distribution, and then we estimate the volume on the volumetric curve, correct? At 90% confidence limits, 50% confidence limits. So we're at those points where we're taking a specific volume curve estimate, just like we would with a grade tonnage curve, and then we're selecting from that, but based on confidence limits, correct?
Andy, it is semi-correct. Yes, we make a curve like I showed you, but the curve is not the confidence. The curve is the probability to find more than that value. So in a greater than company, your lowest value is at your P90. So you're for 90% sure that the amount of volume you will find is bigger than that value. So let me go back to a graph, for example, and I'm using now the graph of the dice. And we just imagine that the bottom there is the million of barrels to find. So we take the right-hand vertical graph, the P90 on the right hand, because I'm a greater than company. So I'm for 90% sure that my volumes will be bigger than 3 million barrels. That is then somewhere here on the graph. I can't tell you how big it will be, but I'm for 90% sure it's greater than 3 million. I'm for 10% sure, somewhere here, that it is greater than 25 million barrels. Because it is between the P90 and the P10, I'm for 80% confident that the real volume I will find will be between my 3 and my 25 million barrels. So the confidence comes in there, but the curve you use to give you a value where you're sure it's going to be greater than or smaller than. So where I say I'm for 10% sure it's greater than 25 is the same as saying I'm for 90% sure it's smaller than 25. Did that answer your question?
Sort of, Peter, but in mining, traditionally, what we would do is to calculate a volume and a variance curve, and then actually put the spread of the estimate around that red line, your probability line. Yeah, the spread would be around that.
That's exactly the complete opposite way as we do it in oil and gas. So you calculate deterministic a volume, And then you say, I don't know, I know this volume can't be right, so I have to put an uncertainty around it. We do it different. We do it different. We say, all the elements we put in there have got an uncertainty. I'm not sure about my average porosity. I'm not sure about my average net to gross. I'm not sure about this. I'm not sure about that. So I multiply all these curves with each other, which gives me a complete distribution curve with all the elements in there. And then I come to this curve. And this curve is taking into account all the uncertainties I have and all the possible outcomes with these uncertainties. And then if I want to be 100% confident that I'm covering all the possible outcomes, I have to go to my P1 and my P99. But that is not workable. So that's why I go to my P90 and my P10, or even some companies go to P85 and P15, yeah, and say these are the numbers I work with. So my low side is my P90, my high side is my P10, and my most likely side is my P50, or my, quite often my mean, which I use. So if you only want one number, you take either your P50 or your mean. But working on one number is not telling your management what the real outcome can be, because there's a 50% chance you're going to be higher than your P50. There's a 50% chance you're going to be lower than your P50. So if you go to your management with one number, you know for 100% sure you're going to be wrong, because you're never going to be that number. So if you want to go to your management to talk about how economic is your project, you say, now on the low side, I take my P90 and I do my economics on that. And on that low side, you probably need less wells, less shafts, mine shafts. And if you go to the high side, you need more wells and more mine shafts. So you need more funding, but you get a bigger return as well. And these, that's why we always go with these ranges. So we give economics for the low side, we give economics for the high side, and we give economics for the most likely side.
I think it's time for a beer, Peter. That's one of the reasons why we have a problem. Well, I have a personal problem in when we look in mining to quote exploration target, which is the very earliest stage with the least amount of information. And then we're asked to quote ranges. And the problem with ranges is that to get within that sort of probability, we're going to end up with, like, it could be 10 billion or it could be 10. So the range is so ridiculously large that it's uninformative. So maybe it's a topic we should throw into the rewrite of SAMREC, Tanya.
Hey, I'm happy to give I mean, this course from Rose and Associates is a whole week. And I've got a reduced course of that I gave in-house to our people there, but maybe it's worthwhile to give a kind of training on this, how we in oil and gas do it, because it has to be realistic in certain ways. And your ranges, the less you know, the broader the ranges are, that's for sure. The more you know, the less the ranges are. And there's a very nice exercise they do with beans, counting beans. And you will learn a lot from it. And maybe it is something in mining we should start to try and implement in mining.
Are there any other questions or comments?
Peter?
Yeah.
This is Tanya. We'll definitely take you up, chat to you further about a course like that. And Andy, that's a conversation we're going to have to take offline with a large bottle of wine.
Very happy to do it in Cape Town.
After the online.
Okay. I see that people want to have these slides. I've got no problems in sending the slides. That's fine.
What we will do is post the presentation, which I've recorded, on a GSSA YouTube video channel. I probably won't have it up today, but it'll be today or tomorrow.
Okay.
And I see there's no more questions or discussion. So Peter, thank you very much for doing the presentation for us. I think it was very professional and very well done. I hope everybody got something out of it. And we'll see you back tomorrow afternoon at the same time for another one of the lecture series. Thank you very much.
Sorry.
I'll end. Yes, Safiso?
Craig, I think Solomon had a comment. Sol, did you have a question? Okay, I think it was accidental. All right, that's fine. Go ahead, Craig.
Okay, with that, I'll close the meeting. Thank you very much, everybody, for attending.
Yeah.
Cheers all.
Okay.
Bye. Cheers.
Thanks. Bye.
Cheers, bye.
Cheers, bye.